Hi everyone. In the previous video I introduced what a buffer is and how it can neutralize any small amount of added acid or base. We analyzed these solutions qualitatively. In this video I want to look at this quantitatively, and I do want to calculate the pH values at different situations. And after I tell you how to do that, we are going to look at this problem where it's asking for the pH of a buffer with added acid, and pH of if we take that acid and now add it to an unbuffered water sample. Okay. This is a problem again that we are tasked with, and they're asking for the pH. We can do this using an ice table and solve for the concentration of H2O plus and then get the pH. But there's another way to do this using what's called the Henderson-Hasselbalch equation, and both the ice table and the Henderson-Hasselbalch uses an extra small approximation. So it's not exactly the pH, but it's a very close approximation to the actual pH. The Henderson-Hasselbalch actually doesn't involve the solving of x, and I'm not going to derive the Henderson-Hasselbalch equation from the ice table, but it can be. Let me give you those equations though, and we'll apply those to this problem. Henderson, Hasselbalch equation. Again, it is coming from an ice table, which does use the extra small approximation. Is x really small? In many cases, I think in all the cases where we work with buffers, yes, because remember a buffer is made with a weak acid or a weak base, and the Ka is fairly small, hence x is going to be small. Anyway, it's derived from ice tables that does, well, my English, derived from ice tables that do use extra small. Okay, let me just get to the equation. The equation is pH equals pKa adjusted for a factor which is log, and this is where sometimes I get confused. The conjugate concentration goes on top, and the weak acid concentration goes on the bottom. Now obviously, or maybe not so obviously, you're going to use this form of the Henderson-Hasselbalch if the buffer is made out of a weak acid. Buffer is a weak acid slash conjugate base buffer. Okay. All right, let me put that in a box. Now, what changes if we're using a buffer made from a weak base and its conjugate acid? For instance, ammonia. And an ammonium buffer, we would not be using this Henderson-Hasselbalch form. We would be using the POH equals pKb plus the log. Okay, it's still conjugate on top, but now on the bottom we have the weak base. And that should work if you're given a buffer made out of a weak base and its conjugate acid. Weak base conjugate acid buffer. All right, why don't we go ahead and work on that problem? Is there anything else I want to say about this? No. Why don't we just jump into the problem? The problem is part A. Calculate the pH of a 1 liter buffer that is 1 molar acetic acid and 1 molar sodium acetate. This is your weak acid. And what was the abbreviation? There are several ways to show the formula for acetic acid. Maybe this is the way you know, with the H in the front. And sodium acetate is the conjugate base, so we replace the H with an Na, C2H3O2. Just keep in mind that this will dissociate into water or in water, and you do get the anion, right? The conjugate base is typically an anion. Okay. Now that's a weak acid, so the majority of this acetate anion will be protonated. It won't let go of that proton. All right, are you ready to apply the Henderson-Hasselbalch? You just got to plug in those numbers there for the weak acid and the concentration of the conjugate base. Oh, we also need the Ka though, right? Because we got to figure out pKa. I could do it down here. Remember, the pKa equals the negative log of the Ka. If we're using the Henderson-Hasselbalch, we need the pKa or the pKb. And pKa equals negative log, and the given Ka is 1.8 times 10 to the minus 5, and that equals log answer equals times negative 1. Let's use 4.74 as the pKa. When we plug into the Henderson-Hasselbalch equation, we have pH equals 4.74 plus log. So this is interesting because the concentrations were 1 and 1. 1 and 1. But put it in parentheses. Maybe you don't even need parentheses. And I can't find my whiteout still. 1.0 over 1.0. Remember, conjugate base on top, weak acid on the bottom. Log of 1 is 0. So we notice here that the pH equals 4.74. There was no adjustment to the pKa. So we just learned something. If the concentration of the conjugate base is equal to the concentration of the weak acid, okay, your pH would equal the pKa. Again, this is an approximation. What do you notice actually? The way this was made most likely is they, how should I say this? They took 500 milliliters of a 2 molar acetic acid and 500 milliliters of a 2 molar sodium acetate, and then they combined them. The concentrations were cut in half because you doubled the volume when you combine them. You notice that we don't consider any equilibrium between the acetic acid and the sodium acetate. We're just picking up directly the concentrations. Okay, so that's why the Henderson-Hasselbalch is not, perfectly accurate, but it's definitely accurate enough to be used in research labs and definitely on an exam. All right, so that's part A. In part B, before I go to a new page, part B is you're going to add some HCl. What's that going to do? In the previous video, we showed that if you add acid, the conjugate base is going to neutralize that acid. So So the concentration of the conjugate base actually should drop. And what happens when the conjugate base grabs that proton? The concentration of the acetic acid would actually rise. Okay, so this is going to be interesting. We have the pH of the buffer already, 4.74. Adding some HCl is going to make the solution more acidic. Okay, so there's no such thing as a perfect buffer, but it's not going to be as acidic as if we had put that acid into unbuffered water, and we'll double check the math for there. Okay, so we predict that the pH would be lower, but not that much lower. So how do we figure out the new concentrations, though, to plug into the Henderson-Hasselbalch? This is part B. Let's see. Well, we have HCl. Oh, how much HCl? 0.10 mole, but we're going to put it into 1 liter, and they said the volume doesn't change. So the molarity of HCl is 0.10 molar, because you divide it by 1, moles divided by liters, and that's the same number. I want to do this carefully. So we have HCl. You know, when I'm hesitating like that, it'll make me a lot more comfortable if I just write out the equation, chemical equation. Plus, that's an acid, so it's going to be neutralized by the conjugate base, and I'll use the salt, NaC2H3O2. Let's see, the acid's going to give up its proton. The conjugate base, which is actually that, with a minus, picks up that proton, and you form HC2H3O2 plus NaCl, and that's aqueous. It will ionize. So what do we have? Do you see how we have the conjugate base and the weak acid? Now, we're going to do a ice table. ICE, because these concentrations are going to change from their original 1 molar when we add the acid, and then we're going to figure out the pH. Okay, from the Henderson-Hasselbalch. Okay, so we are doing an ice table, and for this part of the problem, and this is 0.10 molar. Now the conjugate base was initially 1 molar, and same thing with the acid. So before any reaction takes place with the HCl, 1.0, yep, 1.0, and 0. But actually, this is irrelevant to our calculations. So look at the situation we have here. We have a lot more conjugate base. This is a strong acid, so it is going to give up its proton, and since this is in lesser amount, this is going to go to 0. So we're going to lose all of our acid. That's why buffers are good at buffering. They literally get rid of the added acid, if the added acid was a tiny amount. Now, you could imagine if the HCl was 1 molar, then we would have 0 of each of these. Okay, and then we would have no more conjugate base. And if you have no more conjugate base, you have no more buffer. All right, so the buffers work up to a certain amount of added acid or base. So this is your, minus x plus x. Just be careful of that decimal. And then, yeah, technically you do have 0.10 of the sodium chloride. So now do the math. This is 0. Oh no, this is gone, right? We neutralize all of it by giving up 0.1 molar of this conjugate base. So now we have here 0.90 molar, and now we have here 1.10 molar, and this one also is 0.10 molar. But the numbers that we are really interested in is this and this, the new concentrations that we're going to plug into the Henderson-Hasselbalch. And this one is just telling me that we totally neutralize the HCl. Again, it is a approximation because after there is some acid because of autoionization, but we don't worry about that. Okay. So the Henderson-Hasselbalch, I'm not going to rewrite it. It's in this box right here. We have pH equals, pKa was 4.74 plus log. Now we have our new concentrations. The conjugate goes on top, 0.90. The weak acid goes on the bottom, 1.10. And actually, no, I'm not going to say that. Let's just remember that the conjugate is the numerator and the weak acid is the denominator. Okay, let's do the calculation. 0.9 divided by 1.1, there. And then the log of that answer is a negative number. Okay, that's good because we said that the pH will be lower. Plus 4.74. 4.65 is the final pH. 4.65. It did in fact get a little bit lower when we took the buffer that was originally at 4.74 and we added a little bit of acid, and it became a little more acidic and the pH went down. Now if it wasn't buffered, if we added the acid to an unbuffered solution, what do we get? We get, don't want to show the challenge just yet. How much acid did we add? We were adding 0.10 moles of HCl into 1 liter now of unbuffered water. Okay. Well, you know your equation. HCl plus water goes to H3O plus Cl minus, right? The conjugate base of HCl, the anion. What is that? Well, because this is 100% or near 100% ionization, dissociation, same difference. If you have 0.10 mole in 1 liter, that's starting at 0.1 molar. But all of that 0.1 molar HCl became H3O plus 0.10 molar. You're going to put that into your pH equation. pH equals negative log of the concentration of H3O plus. We're not using the Henderson-Hasselbalch. You know why? We don't even have a buffer, right? The Henderson-Hasselbalch figures out the pH for buffers. This is unbuffered water, and hence log of 0.1, I believe, equals -1, but it's the negative log, right? It's the negative log of the concentration of H3O plus times -1, 1. This is a pH equal 1.00. That's the difference between adding acid into water versus adding acid into a buffered system, buffer solution. All right. So that's neat. We quantitatively showed that a buffer system does work. We could probably guess, though, if we have too much of the acid, we're going to use up all of the conjugate base, and then we no longer have a buffer, and then the pH is definitely going to drop if you add more than 1 molar HCl. Let's take a look at the challenge problem. I'm not going to do this with you. Maybe I'll do this in a future video. But what is the twist here? The twist here is that they want you to adjust the pH to 4.00. So if you look at your Henderson-Hasselbalch, you have pH equals pKa plus log of the concentration of the conjugate divided by the concentration of the weak acid. To be able to get this to be 4.0, I might be giving away too much. 4.74 plus, you got to figure out the ratio. And then you got to figure out how much HCl do I need to get to this ratio. Now, it's not using the same buffer that we had before. It's still acetic acid, but it's not the same concentrations, right? Here I have 1.5 molar acetic acid, and here I have 1.0 molar sodium acetate. So definitely, you can figure out the original pH, but I'm not asking for that, right? We are literally trying to figure out the ratio that will get me a pH of 4. Yeah, I'm not 100% sure how to do this, right? Without putting something on scratch paper. But I want you to go ahead and try it. Let's see how far you can get.